So there's a pretty interesting demonstration called Shoot the Monkey that I really want you to take a look at. So if you get a chance, follow this link. That's a nice YouTube video of shooting the monkey. And the idea behind shooting the monkey is this. If I shoot a projectile at 7 meters per second horizontally, there's a straight line along which the projectile would have traveled without gravity. But because of gravity, the projectile falls. It's very much like what we did in lab. After 1 second, it would fall 5 meters. After 2 seconds, 20 meters. 3 seconds, 45 meters, etc. So the path of the projectile along this red line here, the path of that projectile is going to be below the green horizontal path by 5 meters after 1 second, 20 meters after 2 seconds, 45 meters after 3 seconds, etc. Now I'm simplifying and using an acceleration due to gravity of minus 10 meters per second squared. And I'm showing this to you in 1 second intervals. But what's interesting is the non-horizontal case. In the non-horizontal case, if I shoot a projectile along this blue path, if there was no gravity, it would follow the blue path. But because there is gravity, it's going to follow this red parabolic path. And what's interesting is that the red parabolic path is a distance of 5 meters below the blue path after 1 second, 20 meters below the blue path after 2 seconds, 45 meters below the blue path after 3 seconds, etc. So the distance below the straight line path is exactly the same as it would be if I dropped the ball that traveled down up below that point for a certain amount of time t. So what's happening with the shoot the monkey is that I aim the gun directly at where the monkey is hanging, and the electromagnet causes the monkey to release from its hold at the exact same time the ball comes out of the gun. And so if I aim directly at the monkey along this blue path, no matter how fast I shoot the ball, it's going to hit the monkey. If I shoot the ball super fast, it will hit the monkey high. If I shoot the ball super slow, it will hit the monkey low. And that's what you're going to see when you look at that demonstration on YouTube. Take a look at that and see what you get from there. Okay, the next thing we want to talk about is uniform circular motion. Now this term uniform is very important. Uniform means constant. So constant speed and a constant radius. Of course, if it is truly circular motion, the radius must be the constant. That's what a circle is. But uniform means it's moving around the circle with the same speed. So there could be times when it's non-uniform circular motion, if I'm speeding up or slowing down as I go around the circle. A real good example of non-uniform circular motion is if you're on a playground merry-go-round. You push the merry-go-round, you go faster and faster, you jump onto the merry-go-round, and as the merry-go-round spins, it slows down. So your speed is increasing as you push it, and then it's decreasing as you stop pushing. A uniform circular motion would be a merry-go-round at an amusement park. Horses get going, they make it up to speed, and they move around in that circle at a nice constant speed. And the radius is constant. You sit on your seat in the merry-go-round on your horse, and your distance from the center of that motion is the same. So that's uniform circular motion. So here's a circle. I can have an x and a y axis, and there's some radius r as I'm on that circle, and I'm moving around the circle. Could be clockwise, could be counterclockwise, with some speed v0, and that's a constant speed. Now remember that velocity is tangent to the path, and tangent to a circle is always perpendicular to a radius. So the velocity vector is always perpendicular to the radius vector. So if I go over here to a different point, it's the same radius but a different radius vector because it's pointing in a different direction. The velocity is also pointing in a different direction, and it's going to be perpendicular to that radius vector. Now what's interesting to note, let's take a look at the velocity right here at the positive x-axis. That velocity is going to be up. It's going to have some magnitude v0, some direction straight up. If I look at the velocity at this location, halfway between the x and the y-axis, same magnitude, because remember the speed is the same, but in a different direction. So if I label this 1 and this 2, velocity 1 and velocity 2, then there is an acceleration. But the average acceleration, when we think about this, remember it's final minus initial. But minus initial would be in this direction. Okay, it's the same as the initial velocity, but the initial velocity was up, so minus means point down, and then that will be the difference there. So if this is v0 2, this is v0 1, This right here is v02 minus v01. But that direction is very important because that's going to be the same as the direction of the acceleration. So this is the average acceleration, change in velocity as far as direction goes. So if everybody's uniform from here to here, that would be about there. And if I look at that as I've drawn it, points in that direction. And so since it points in that direction and its acceleration, I like to do accelerations in red, you'll notice the acceleration here points towards the center. So when I talk about uniform circular motion, I always have a centripetal. Centripetal means center-seeking acceleration. Not centrifugal, we'll talk about that later. It's a centripetal acceleration. That means center-seeking. Turns out the magnitude of the centripetal acceleration, I might write just as a sub c, is equal to v squared over r. Now we won't derive that in this class, but you might in a later on course. So the centripetal acceleration is equal to v squared over r. Since it's not speeding up or slowing down, there's no acceleration tangent to the circle. That acceleration doesn't exist. It's not speeding up or slowing down. There's only turning. And that also tells you this must be along a radius. Because if there was even a component along the direction of motion, or backward from the direction of motion, that would mean it was speeding up or slowing down. But it isn't. So that acceleration can only turn the object. It cannot speed it up or slow it down. So centripetal acceleration is always along the radius vector in uniform circular motion. Again, the magnitude is equal to v squared over r. So the bigger your speed, the higher that acceleration. The smaller your radius, the higher that acceleration. The bigger your radius, the lower that acceleration. If you take a drive sometime, if you make a turn at high speed, you can feel yourself needing to hold on tight to make that turn. You can feel the acceleration towards that middle. And it's large if you're moving at a high speed or in a tight corner, which is a small radius of curvature. It's not so bad if you have a large radius of curvature or if you slow down. We'll talk more about those forces in a later chapter. Some other terms that we might talk about now. If I'm going around the circle, I might travel a distance around the circle. And you may recall from geometry, the distance around the circle is called the circumference. So that's equal to 2 pi times the radius. That's the distance around the circle. The time it takes to go around the circle is often called the period of the circle. That's the time it takes to make one full revolution. And I'll give that a capital T. And so the speed at which I'm going around the circle, speed is equal to distance over time. That's going to equal 2 pi r over the time, the circumference divided by the time. And the speed is uniform, so even if I went 2 circumferences, 2 periods, it's going to be the same value. Given that, the centripetal acceleration, remember, is v squared over r, but v is equal to 2 pi r over the period, and we'll square that and then divide by r. So that's 4 pi squared r squared over the period squared, all divided by r. This r cancels one of those r's, and we get 4 pi squared r over t squared. That would be the centripetal acceleration. So if we increase the radius without increasing the time, we get a larger centripetal acceleration, but that makes sense. If I increase the radius but I take the same amount of time, I've got to speed up. In other words, to make that circle, which is larger, in the same amount of time, I've got to travel faster. 2 pi over t is often referred to as the angular frequency or the angular velocity. In other words, 2 pi is a full circle and t is the time it takes to go around the full circle. So this is angular distance. 2 pi radians is how much of an angle I've gone through in going through a full circle. So this is the angular velocity, and the angular velocity is generally given in radians per second. And so the centripetal acceleration can be written as 2 pi over t squared times r. The angular velocity or the angular frequency squared times the radius. Angular frequency is oftentimes denoted with the Greek letter omega. So that's omega. Omega looks like a W with a little wing on it. That's omega. So omega squared times the radius. So these are just some other terms that you may see as you're reading through the material. So now that we know a little bit about circular motion, let's take a look again at average and instantaneous acceleration. So let's assume I have some path, and the object is moving along that path. At some point along the path, it'll have a velocity, always tangent. So there's the velocity tangent to the path. There could be a velocity here also tangent to the path. Let's label that v1 and v2. They're not in the same direction. They may or may not have the same magnitude. It doesn't matter. But there's also going to be an acceleration. Now the acceleration could be in the direction of the velocity, could be opposite the direction of the velocity. If it's in the direction of the velocity, then it speeds it up. If it's opposite the direction of the velocity, it slows it down. So let's point the acceleration in this direction. This is tangential to the curve, so I'm going to label it AT for tangential. The other part is very similar to the centripetal acceleration. It's what turns the object, and it's perpendicular to the path in towards the radius of curvature. So I'm going to call this A sub n for normal. Normal means perpendicular. That's another term for perpendicular. Normal, perpendicular, orthogonal all mean at 90 degrees. And so the net acceleration in this case is the vector sum of the tangential portion plus the normal portion. So this would be the acceleration right there. That's the net acceleration. It's got a tangential component along the curve and a normal component in towards the center of the curve. In a similar fashion, then if I went over here, there's an acceleration, and I'll pretend it's slowing down. So there's an acceleration in that direction. That's the tangential acceleration. And there's an acceleration in this direction. That's the normal acceleration. And so the net acceleration at this location would be right here. That's the acceleration vector. Normal component, tangential component. Notice over here the tangential component is not along the x. The normal component is not along the y. In general, will not be along the x and the y. They happen to be here just the way I happen to draw that. But in general, they'll have their own directions, and they'll always be perpendicular. The normal and the tangential are always perpendicular. Have to be. Normal means perpendicular to the tangential. So they'll always be perpendicular. It turns out A sub n is equal to v squared over, I'm going to call it rho. This is the Greek letter rho, and it stands for the radius of curvature. But keep in mind, this radius of curvature at this location is not the same as this one. So the radius of curvature can change. The acceleration tangential is how fast you're speeding up or slowing down. So A tangential is basically equal to v, not v vector, but speed dot, the derivative of speed with respect to time. We won't worry about that too much. If I tell you it's slowing down or speeding up by a certain amount, I'm giving you the tangential value of the acceleration. If I give you the radius of curvature and the speed, you can calculate the normal component of the acceleration. So you have to be given those terms. So keep in mind, speeding up or slowing down, that's tangential acceleration. Turning or around a radius of curvature, that's normal acceleration. So just as an example, assume I have an airplane flying in a circle, and the circle has a radius of curvature of 275 meters. So here's the airplane flying in the circle. Radius of curvature, 275 meters. I have a speed of 87.7 meters per second. So r is equal to 275 meters. This is what I'm given. Speed is equal to 87.7 meters per second. Notice no vector there. That's a speed, not a velocity. The speed is increasing at a rate of 5.52 meters per second squared. So A tangential equals 5.52 meters per second squared. I want to know the magnitude of the acceleration. Well, in order to know the magnitude of the acceleration, I have a normal and a tangential component. So I know that the tangential component is 5.52 meters per second squared. The normal component is v squared over r, v squared over rho, but the radius of curvature is 275 meters. So this is 87.7 meters per second. That's going to be squared, divided by 275 meters. So this is 7691.3 meters squared per second squared. Divide that by 275 meters, and I get 28.0 to 3 significant digits, and that's meters per second squared. Notice I've got meters squared per second squared divided by meters. That's the same as meters squared per second squared times 1 over meters. One of those cancels, but 1 meter is left over. And so I get meters per second squared, which is an acceleration. So the magnitude of the acceleration is the tangential component squared plus the normal component squared, all under the radical. So that's going to be 5.52 meters per second, quantity squared, plus 28.0 meters per second squared, quantity squared. This is meters per second squared here, all under the radical. I have more accuracy than 28.0 on my calculator. And when I work all that out, I get 28.5 meters per second squared. Not much different than the normal component, but that makes sense because this is a much bigger side at 28 than that is at 5.5.